So what's RPI? Well, when we formulated this theory, we needed a direction for the collinear line, or for the collinear particles, n. And then we needed an auxiliary vector, n bar. And we formulated the whole setup in terms of this n and n bar. But having vectors like that we write down, that breaks Lorentz invariance in the same way that specifying v mu in HQET breaks Lorentz invariance. So if you say that m mu nu is the set of Lorentz transformations, the usual 6 generators that are antisymmetric, then the ones that are broken are these ones. And there's 5 of them. And the one that's not broken is this one, which corresponds to rotations about the 3-axis, or the axis specified by n. Okay, so those rotations would act in sort of the components of these guys that are 0, if you like. So there's no issue there. And these guys are the guys that are connected to the pieces that were non-zero in general. So there's going to be a larger, because there's sort of 5 things here, and because there's 2 vectors, it's going to be a larger set of reparameterization symmetries than in HQET. And there's actually, first talk about just the n and n bar themselves. There's 3 types of reparameterization invariance that would leave n squared equals 0, n bar squared equals 0, and n dot n bar equals 2. And those were the formulas that we were using over and over again, really. Everything else was just convention. OK? So what are those 3 types? Well, we could take n, and we could change it by some amount in the perp direction, and leave n bar unchanged. And since n bar dot something perp is 0, that would be that would satisfy this. Or we could do the opposite. That would be type 2. So don't change n, and change n bar. And so this is 2 transformations. There's 2 things specified by this perp guy, and 2 here. And then there's one more, which is called 3. And this one, let me write like this. It's a simultaneous transformation of these 2 guys, where I just do a multiplicative factor. Well, multiplicative factor is not going to change the fact that the square of something 0. The place where the normalization comes in is this n dot n bar. And if I just rescale them both by an opposite amount, then that remains satisfied as well. So I've formulated this in terms of I'm going to think about this as an infinitesimal transformation for delta perp, infinitesimal for epsilon perp. I could also expand this exponential and think of it as infinitesimal, but it's even the finite one's easier. So let's just think of the finite transformation in the last one. Now, this is an effective theory. So whenever we think about transformations, we should think about power counting. We just spend a lot of time thinking about that for gauge symmetry, and we should think about power counting here too. Did you have a question?
What about large transformations which like rotate the whole axis?
Yeah. So we're just about to talk about how big things can be. So the power counting, that's the right power counting for these guys. So these things are infinitesimal or finite, but they also have some counting in a different space, which is the power counting space. And the right power counting for these guys is as follows. So this means I can make arbitrarily large transformations in a power counting sense of type 2 and type 3. There's no constraint. That's what this means. So maybe that's easier to swallow. This one, there is a constraint. And the reason that you can think of there being a constraint, I can give you a simple example. And then you'll see how you would derive the other things as well. So think of n dot p. If you transform n dot p, that becomes n dot, think of this as n mu p mu. That becomes n mu p mu plus delta perp dot p perp. So this is order lambda squared, so this better be order lambda squared, but this momentum here is order lambda, so you need to have a power counting for the delta perp that makes it of order lambda in order to keep the transform guy the same size as the guy you started with, because I don't want to consider transformations that would take me away from my power counting, that would violate it. So imposing that this thing is of order lambda squared says that this is true. If you go through the same logic for the other guys, well, the n bar component was order lambda 0, so you can make the epsilon perp of order lambda 0. It doesn't cost you anything because there's no constraint. You're not making something that would mess up the power counting. All right. So what does this correspond to physically? So type 3 is actually pretty simple. Type 3 is like a boost along, if you think about our back-to-back vectors, type 3 is like the analog of a boost, but you're transforming it in the passive sense of transforming the axis. And what the outcome is very simple. It just implies that any operator that has an n must have a corresponding n bar sitting next to it, effectively. So I'll give you some examples. So really, if you have, let's just say it this way, if you have an n bar mu in the numerator, then you either have a corresponding n in the numerator or you have an n bar in the denominator, since we could have n bars in the denominator. And that was showing up in some places. Those are the two possible ways of compensating for the transformation. So it's just like a simple counting that you have. So if you look at our LC0, we had various terms. One of them was n bar slash 1 over I n bar dot d. So here we have an n bar in both the numerator and the denominator, and that compensates for the transformation. And then in another term, we had an n bar slash n dot d. And then that again is invariant under this type of transformation. What about type 1 and 2? So type 1 is the following. So think about these guys as in this kind of language where they would be back to back. We're trying to describe the physics in this cone for the collinear particles. And n was the vector that was pointing inside that cone. What this is saying, type 1, is that I can rotate that guy. And as long as I'm not rotating it by too much, i.e. I'm rotating it by a small amount of order lambda, which you can think of as staying inside the cone, then I can describe everything equally well by some other vector that lives in that cone. And I can decompose the momenta and the modes in terms of that vector, and it will work equally well. OK, so that's what type 1 is physically doing. And so you're not making a large transformation here because you want to still be inside the cone. You still want something that's pointing in the collinear direction. Type 2 is related to the fact that this n bar vector was just an auxiliary vector that we used to decompose things. We didn't really care about it. It didn't have a strong physical motivation. It was just needed because we're using light cone coordinates. So I can make a very large transformation of that guy. So here's a large transformation. And I can use some other guy. And we gave you an example earlier, which was 3221 as a possible value for the n bar. And that's something that you could think of getting to by a finite type 2 reparameterization transformation. OK, so that's the kind of picture for what these transformations are. And we will finish up talking about them next time, and we'll show that actually this additional term that we could write down in the Lagrangian is actually ruled out by reparameterization symmetries.